Hello and welcome to this final test that we're going to be talking about tests of group means, and this is the Way Anova, and we will go through the same kind of set of parts for this particular statistical test. So in terms of the Way Anova, we start off with the same idea in terms of the population, and then we take some kind of simple random sample to draw our sample, and really in a way we're drawing three or more samples, and so we have sample size 1, sample size 2, sample size 3. Sometimes those samples are each the same size, but each one of those samples then has an x bar 1, x bar 2, x bar 3, 3 bar 3, standard deviation 1, standard deviation 2, and standard deviation 3. So each one of those subsamples from our main sample has these measures. And ideally, we've not only measured them accurately and taken our simple random sampling, but then whatever we find, we can infer back to our population parameter. So let's take a look then at what the data entry looks like for a Way Anova. And again, here's our golden rule, which is that each row in the data set, and this is your Excel data set or this is a SPSS data set, but each row represents one person. And so these two things that we've measured, the continuous variable and what group they're in, are for each person. Now the person could actually be a hospital, it could be a country, but whatever it is that is that unit of measure, all of the information for that individual entity falls on the same row. Now what you'll notice then is that we have a continuous variable similar to what we've been looking at in all of our other statistical tests. Ooh, just got tiny. But this time we have three or more categories, and so here we have category 1, here we have category 2, here we have category 3, and so on. And it could be that there's a category 4 and a 5 and a 6. It's not limited to 3, but oftentimes we talk about a Way Anova in terms of having 3 or more categories. Mathematically, the thing you need to remember is that a one samples t-test is really the same as a Way Anova with only 2 categories. So it would not technically be wrong to run a Way Anova, but you'll notice that there are a few differences. So if you're given the choice between the two and you have only 2 categories, then an independent samples t-test is a better answer to that question. So here we have a whole bunch of individuals who have been measured, both their continuous variable, and we've recorded what category they fall into. And if we were to compare this to the textbook example that you've looked at, there was an example where we measured the continuous variable heart rate as an indicator of their stress level for 3 different groups. One had a pet present, so that's this group 1. One had a friend present, and that's this group 2. And then one had neither, and that was group 3. And so each one of those has a histogram, a mean, a standard deviation, and all of the sample sizes were 15, by the way. So we had a total sample size of 45. But each one of these groups then will have something measured about them, the x bar, the standard deviation, and so on. And if we were to draw that, then like we did for the independent samples t-test, what that would look like is very similar, except now instead of just having 2 groups, we have 3 groups. And so I think in that particular example with the pet, the heart rate over here on the left hand side as a surrogate for stress was the lowest. If we took all the 15 data points, kind of put them there, and here's the middle of it, was the lowest. The friend was the highest, and so there would be the middle there, and the neither was kind of somewhere in between. And the grand mean, let's see if I can draw it pretty close to what this study actually found. Let's draw it in a different color. We don't get a different color right now. Was slightly below the group 3. And so what we have then is that we want to measure, in other words, sort of the difference between that grand mean and each of these. Remember, we're talking kind of about signal to noise. How far are these spread out compared to how far they are away from that overall mean for the whole entire group. And so that's what we're talking about when we're thinking about a one-way ANOVA. Now, let's go ahead and look at what the hypothesis then looks like. What we saw as a hypothesis for a one-sample t-test is that mu1 is equal to mu2, and that's true here, except now we have a third group, so I'm going to say equals mu3. So all three of them are equal, and the alternate might catch you off guard a little bit, so let me write it out in full. At least one mean is different. And some people might think that the alternate should be mu1 is not equal to mu2 is not equal to mu3, but the problem with that is that we don't actually know which one is different. It might be that one of them is only different from one other one. And what we're doing with the one-way ANOVA, because of the way the F-test is set up, is we're doing an overall test about all of the means at the same time. So this is the test for this is a one-way ANOVA, and the assumptions are the same as an independent t-test: normality and equal variances. And if you remember back here, we had both x bars, and so that's normality of those distributions, and we had standard deviations, and this is where we need to have equal variance of those distributions. In other words, what we can't have is to have one of the distributions really spread out and the other one really close together. So I'll get rid of those just because they're I gotta talk fast if my pencil's gonna die. So the test statistic is an F statistic, and that is mean square between divided by mean square within. Remember, we learned about that in terms of location and spread when we learned about the F distribution, kind of a signal to noise. The critical value, again, we need to decide ahead of time what our decision point is, and then based on that F statistic we calculate a p-value that goes with it. Now the interesting thing that happens is that when I do this one-way ANOVA, I am testing all of those means together at the same time. I'm not testing just one combination. So only if this p-value is less than 0.05 can I go on to test these 95% confidence intervals that compare mu1 to mu2 and mu1 to mu3 and mu1 2 to mu3. So if I do reject this overall test statistic, then I can go ahead and do what's called least squares difference or Bonferroni, where I test each pair. Now let's go ahead and skip over that part really quickly, because I will talk about kind of like the post hoc tests, but we do need to, based on that particular decision, we do need to decide whether to reject or fail to reject the overall or omnibus ANOVA F test. And so for this particular example, it was rejected. We reject the null, the overall null. So it's unlikely for these three samples with the observed differences to have been randomly drawn from target populations that didn't have any differences. So the way we write that in APA format is there was a significant effect of companion choice on heart rate. There are some ways that you can write it where you can actually put in the mean for each one of those and standard error. But here's the F test, and remember how it has 2 degrees of freedom? This first number is the degrees of freedom of the numerator, and the second one is the degrees of freedom of the denominator. And here's our F value. That's quite a bit bigger than 4.0, so it'd be pretty easy to see how this p-value is so large for that. So let's go back and talk really quickly about those post hoc tests. In other words, I want to be able to test each of these combinations. Now, remember how we had the problem where we had multiple comparisons, and so that family-wise error, type 1 error rate becomes inflated? So what we need to do is we need to decrease that probability of making that mistake. And so we have a couple of different tests that do that in different ways. One of them is called the least significant difference, or LSD. I've seen it listed both least significant difference and least squared difference in different textbooks, but it's a very common one. However, it is unadjusted. So the least squares or least significance difference, we only do this for a priori or ahead of time hypotheses that we're wondering about. So basically this does a t-test. T is equal to x bar 1 minus x bar 2 divided by standard error of x bar 1 minus x bar 2. So I hope you recognize that as just a plain old independent samples t-test. The 95% confidence interval is exactly what we looked at in terms of the t-test. It is unadjusted, and so it has that problem of inflating that type 1 error. Bonferroni, on the other hand, takes that, basically the essential thing is that it takes that 0.05 error rate that we want, and it divides it by the number of groups that we have. And so there are a couple of ways to thinking about it. You can take the least squares difference and multiply it times the number of groups to get the Bonferroni, or you can take the 0.05 and divide it by the number of groups to find a different lower maximum cutoff for this critical value. But essentially it's the same thing, where now we have an adjustment so that the total type 1 error for all of the tests combined is going to be equal to whatever critical value we've set up for in advance. So a lot of the same things apply once we have rejected this initial null hypothesis for a one-way ANOVA test. Just we're doing multiple tests over and over again for each of the different combinations, because a lot of times that's what we're really after is, once we know that dog, friend, and none are different from each other, or at least one of them is different, we want to know which one it is. So that's where the least significance difference or the Bonferroni, there are a whole bunch of different mathematical corrections that can be made for that. So one last thing before I go from this particular topic is we have these two assumptions, and I want to talk about the assumption of normality and equal variances a little bit. What happens when the assumption of normality is violated? And I think we've already looked at that in the past, and we've said, well, one of the things you can do is you can do a transformation. And the interesting thing that happens is that if equal variances is also violated, then often the same transformation that works to fix normality also fixes equal variances. And so the math behind those fixes a lot of times will fix both of them. Another thing that you can do is you can do a non-parametric test. And both of those things are beyond the scope of our class right now, but just know that there are some things that you can do to fix them. So even though we don't do them in our class, there are ways to kind of make sure that the analysis we do is correct. One of the things that a lot of times people will ask is, how do you even know if the variances are equal? And there are three different kind of ways that the textbook talks about, so I'll say a little bit of something here. One of them is if you create box plots, your interquartile ranges, remember how they have the median, they have the whiskers. If the range from the 25 to 75% is approximately the same height for the different groups, then that's a good kind of eyeball method to see if the variances are equal. Another way is to look at your standard deviation, and if none of them are more than twice as big as others, so if you have one standard deviation that's a 2 and another one that's a 3, that's probably still fine. A lot of these tests, like the Way Anova, are pretty robust against small differences, but if you have a standard deviation of 2 for one of your groups and a standard deviation of 10 for another group, then that certainly would violate this times 2. The final way that you can test for equal variances is something called Levene's. And it's interesting that this assumption of equal variances is violated so often that the independent t-test automatically even creates a Levene's test as part of the test that it runs. So if you run a Levene's test and you get a p-value that is less than 0.05, what that means is that variances are not equal. And if you get a p-value that is greater than 0.05, that means that the variances are reasonably equal. They're not exactly equal, but they are not significantly different from each other. Now, the same kinds of problems happen with equal variances as happen with normality, and that is if you have way, way, way small of a sample, so less than about 30, then your test may not be powerful enough to be able to pick up on a difference if it is there. And if you have a sample size that's really big, like greater than 100, then it may be so sensitive that it will say that the variances aren't equal when in fact they really are pretty close. So often what you want to do is a combination of those three. Start by looking at the interquartile range or the standard deviation as a good starting point, and if you don't see anything terribly severe, then the Levene's probably isn't going to help you very much. But if you're kind of on the line, you're like, well, I'm not sure, and you have a sample size, I would say somewhere between 30 to 100, then the Levene's test is going to work pretty well to help you out. Again, very similar to the central limit theorem, as you kind of move into the larger and larger and larger sample sizes, we generally don't worry as much about the assumptions of normality and equal variances, although they still are important. The tests that we do are pretty robust against at least minor deviations from meeting the assumptions. And so as long as you don't have anything that's terribly severe, then you can probably go ahead and do the test and then maybe even compare it with the results that you get from a transformation or a non-parametric analysis. So those are some of the hints about assumptions. One final thing that I'd like to point out is a lot of times in textbooks they'll say that there is an assumption of independence. And that is a way of, that's one of the features of how you drew your sample. Did you draw a sample so that the individuals that are in your sample are independent from each other? Were they selected independently? In other words, did they each have an equal chance of getting into your sample? And so if you see something listed as independence, as one of the assumptions, then that's perfectly fine. That's a good way of thinking about it. I would say in the same vein is you want to have accurate measurements. If you don't draw a representative sample from your population and you don't measure things accurately, then it doesn't matter. You can't transform that out. You can't fix that. So make sure that your study design, your sampling technique, your measurement technique is valid, so that the results that you get can then be inferred back to the population parameters. Thank you for joining me.